Have you at any point considered the profound struggle between an enraged star and its planet? A youthful planet, close to a red dwarf star, changes in shocking ways each time it circles the star. When NASA's Hubble telescope initially observed it, the planet's atmosphere appeared to be safeguarded. However, around 18 months later, Hubble discovered that the star's strong energy waves, driven by stellar winds, were pulling the planet's hydrogen atmosphere away. The planet's baffling atmosphere presents a riddle, undergoing dramatic shifts from one orbit to the next. But why is this red dwarf star unleashing its high-energy fury on its own planet? Join us in this video as we explore NASA's incredible observations and unravel the fascinating mystery of an enraged star. The Hubble telescope, orbiting Earth, can detect when a distant planet passes between its star and Earth by capturing the star's light. This movement causes the star to appear slightly dimmer temporarily, signaling that something caused the brief dimming. This technique was how scientists initially discovered the planet OMCB in 2020. However, for that initial discovery, it was NASA's Spitzer and TESS telescopes that spotted it first. Since then, Hubble has made its own OMCB observations. Scientists noticed something more intriguing than just changes in starlight during a typical transit. By closely examining the light waves, they found the dimming of starlight from OMCB was much deeper than expected, extending beyond the planet itself. This was not solely due to the planet passing in front of its star. OMCB orbits its host star, OMC, every 8.46 days at an incredibly close distance of just 6 million miles, 9.6 million kilometers, about 1/10 of the distance between Mercury and the Sun. This system lies only 32 light-years from Earth. The star, classified as a red dwarf, is notable for its extreme nature and is one of the youngest known stars, with an age of around 23 million years. Despite its proximity to the star, the planet experiences significant fluctuations in atmospheric loss during each orbit. Red dwarfs, the most common stellar objects in the Milky Way, are known for their intense magnetic fields and powerful stellar flares. These stars can release energy exceeding our Sun's emissions by up to 1,000 times. It's 23 million years old, which is incredibly young, essentially a baby star, said Key Rockcliffe, the lead author of a study on the new Hubble findings and an exoplanet scientist at Dartmouth College. Astronomers are excited because OMCB provides a glimpse into the energetic, tantrum-like early years of a red dwarf, one of the most prevalent types of stars in the Milky Way. Surprisingly, the cause of this massive activity lies in the material escaping from the planet's atmosphere, gradually fading into space. This remarkable finding reveals a phenomenon called atmospheric evaporation, driven by the red dwarf's intense high-energy outbursts. Hubble's data showed that these strong energy blasts, referred to as stellar winds, are responsible for the changes. The star's intense radiation strips the planet's atmosphere, creating a turbulent environment. Scientists believe the changes in OMCB's evaporating atmosphere might be due to its unpredictable red dwarf star. Perhaps a significant energy burst from the star made the escaping hydrogen invisible to light, or maybe the strong forces from the star influenced how the planet's atmosphere drifts away, causing it to appear and disappear at different moments. What's fascinating about OMCB's atmosphere is its inconsistency. Sometimes, the star appears agitated, affecting the planet, while at other times, it's calm and causes no changes. Rockcliffe and her team hypothesized that the planet's gravitational force caused some of its material to separate from its core, leading to this escape. She described it as the material being swept away dynamically, offering a captivating glimpse into the intricate dance of this distant cosmic pair. I remember when I first created the light curve of this planet with our Hubble data and saw that the transit occurred well before the expected time, Rockcliffe said. I immediately thought, well, I must have made a mistake. However, no matter how many times I reanalyzed the data using different methods, the result was the same. When atmospheric evaporation was first observed, it was in planets known as hot Jupiters. These are some of the rarest exoplanets in the universe, essentially hotter versions of Jupiter, because they orbit very close to their stars, making them incredibly warm. However, what we haven't often found are planets like OMCB with such dramatic atmospheric behavior. To provide a clearer picture, Rockcliffe explained that using such limited data to understand the entire process is like extrapolating the daily experiences of the working class from the life of a wealthy individual. Atmospheric escape, she noted, is one of the most dynamic evolutionary processes for most exoplanets. This work could help scientists unravel the nature of worlds beyond our solar system, where they exist, and perhaps even guide us toward understanding their habitability. Red dwarf stars, the most common in the Milky Way, are believed to host many planets. Yet, the rapid and unpredictable changes we see in these stars pose a perplexing challenge for astronomers. Rockcliffe emphasized, there's a major mystery about how exoplanets might be losing their atmospheres. When we study these distant planets, one big question stands out. What's causing their atmospheres to evaporate? Is it the intense radiation from their star, or could it be heat from the planet's own hot, youthful core? It's important to note that scientists observed a planet's atmosphere escaping ahead of the planet itself. What's even more curious about the atmospheric changes in OMCB is their irregularity. It's as though the star has mood swings, sometimes agitated, influencing the planet, while at other times calm and undisturbed. My instinct tells me this behavior is intricately connected to the atmosphere's interaction with OMC's stellar winds, Rockcliffe said. OMC's stellar winds might be causing turbulence as they interact with the atmosphere, leading to this time-variable outflow of hydrogen gas. She also pondered the planet's distant future based on Hubble's observations. While these ideas are still in their early stages, a few intriguing possibilities stand out. If the planet loses its entire atmosphere and is stripped to its core, it could resemble Mercury. However, if it retains some of its lower atmosphere, it might develop into a world with unique atmospheric conditions, perhaps with thick clouds or an entirely different climate system. OMCB and its fiery host remind us of the countless wonders and mysteries waiting to be uncovered beyond our cosmic neighborhood. Could the extreme behavior of red dwarf stars like OMC influence the habitability of their planets, including the potential for life to emerge? As we continue exploring the vastness of space, the mysteries surrounding exoplanets and their stars remain a focal point of modern astronomy. The study of exoplanets, worlds outside our solar system, has surged over the past few decades, revealing an incredible array of curious and surprising planets. While the discovery of planets orbiting stars like our Sun has garnered much attention, the most fascinating and often misunderstood planets are those orbiting red dwarf stars like OMCB. Red dwarf stars, being the most common type of star in the Milky Way galaxy, make up around 70 to 80% of the stars in our universe. These stars are smaller, cooler, and less luminous than our Sun, but have extraordinarily long lifespans, lasting tens to hundreds of billions of years. Despite their abundance, red dwarfs present unique challenges for scientists trying to understand how planets in their habitable zones could support life. Unlike the Sun, which is relatively stable, red dwarfs are known for their volatile behavior. They are characterized by powerful solar flares and intense magnetic activity. These flares release massive amounts of radiation and energetic particles, which can have significant effects on planets orbiting too close to their stars. For planets like OMCB, situated at a dangerously close distance to its star, the effects are particularly dramatic. The planet's atmosphere is subjected to constant assault from stellar winds and radiation, leading to atmospheric loss. This makes it increasingly difficult for such planets to maintain stable conditions that could support life. Interestingly, OMCB's situation offers scientists a unique opportunity to study atmospheric evaporation and its long-term effects on planetary evolution. By examining the interactions between the planet's atmosphere and its host star, researchers can better understand how exoplanets evolve in extreme environments. This research also raises important questions about habitability. Red dwarfs are known to have many planets within their habitable zones, but their volatile nature could make these zones far less hospitable than previously thought. The constant radiation and stellar flares could strip away atmospheres or create conditions too harsh for life to develop or survive. Rockcliffe and her team plan to continue studying OMCB and its fiery host star using tools like the Hubble Telescope and other upcoming missions. They hope to uncover more clues about the processes shaping exoplanets and their potential for habitability. These findings could help us better understand the dynamic interplay between stars and their planets, offering valuable insights into the nature of worlds beyond our solar system. The discovery of OMIC B has significant ramifications for our comprehension of the universe and the probability of life beyond Earth. The instance of OMIC B highlights the staggering intricacy of planetary frameworks and the dynamic connections among stars and their planets. It likewise emphasizes the need for continued investigation and study of exoplanets, especially those orbiting red dwarf stars, as they constitute the majority of planetary systems in the galaxy. As technology advances and new telescopes, like the James Webb Space Telescope, JWST, continue to deliver remarkable data, the mysteries surrounding exoplanets like OMIC B may become clearer. For now, OMIC B serves as a fascinating example of the complex and often tumultuous interactions between stars and their planets, offering glimpses into the extraordinary variety of worlds beyond our solar system. The proximity of OMIC B to its red dwarf parent star exposes it to intense stellar flares and winds, posing a genuine threat to atmospheric stability. Researchers have observed that such stars can strip away the atmospheres of neighboring planets, a phenomenon that could significantly impact the planet's ability to retain liquid water and support life. The challenge for astronomers lies in understanding the specific processes that lead to this atmospheric erosion and how these processes vary from one planet to another. While planets closer to red dwarfs are more vulnerable to these effects, factors such as a planet's size, magnetic field strength, and atmospheric composition can influence the degree of atmospheric loss. For instance, planets with strong magnetic fields may be better equipped to protect themselves from the intense radiation emitted by their stars, while those lacking such defenses are more prone to atmospheric loss. One of the significant puzzles scientists face is determining whether a planet can maintain its atmosphere over long periods. Some models suggest that planets orbiting red dwarfs could experience a runaway greenhouse effect, where the star's radiation continuously heats the planet's atmosphere, preventing the formation of a stable environment. This process could lead to a Venus-like scenario, where the planet becomes so hot that any potential for liquid water is lost, effectively extinguishing the possibility of life. Other planets might undergo a more gradual process of atmospheric escape, where the outer layers of the atmosphere are slowly eroded by stellar winds over billions of years. Ultimately, the fate of these planets is intrinsically tied to the behavior of their host stars. Despite the apparent challenges posed by red dwarfs to planetary habitability, scientists remain optimistic about the potential for life in these systems. Some researchers suggest that even if planets in close orbit around red dwarfs lose their atmospheres, they could still harbor subsurface environments where life might thrive. These underground habitats could be shielded from harmful stellar radiation, offering a sanctuary for microbial life or, in rare cases, more complex organisms. The discovery of extremophiles on Earth, organisms that thrive in extreme conditions such as deep-sea vents or acidic hot springs, has broadened scientists' definitions of what constitutes a habitable environment. In some ways, red dwarf stars might even offer unique opportunities for life to develop in ways we have yet to imagine. For example, the habitable zone around a red dwarf, where conditions are suitable for liquid water, is much closer to the star than it is for sun-like stars. This means planets in the habitable zone of red dwarfs are likely tidally locked, with one side always facing the star while the other remains in perpetual darkness. While this presents challenges for the planet's climate, it also creates unique conditions, such as the possibility of vast stable regions of liquid water near the planet's terminator line, the boundary between the light and dark sides. These regions could be prime candidates for supporting life, and may even be more stable than the rapidly changing conditions on the planet's sunlit or dark sides. Furthermore, The frequent stellar flares emitted by red dwarfs could serve as an unexpected fuel source for life. On Earth, solar flares are associated with space weather events. But around red dwarfs, these phenomena are much more common and intense. Some scientists speculate that the energetic radiation from these flares could drive chemical reactions beneficial to life, acting as a catalyst for complex biochemistry in ways we do not yet fully understand. As astronomers continue to observe red dwarf systems with increasingly sophisticated tools, new insights are emerging about the potential for life in these distant worlds. Advances in telescope technology, such as the launch of the James Webb Space Telescope (JWST), are providing unprecedented views of exoplanets in the habitable zones of red dwarfs. The JWST's ability to analyze the composition of distant atmospheres and detect the presence of chemicals like methane, carbon dioxide, and oxygen could help scientists determine whether these planets have the right conditions for life. If signs of life are detected, it would be a groundbreaking discovery, potentially ushering in a new era in our search for extraterrestrial life. Meanwhile, researchers are focused on studying the behavior of red dwarf stars in greater detail. By understanding how these stars interact with their planets, scientists hope to unlock the secrets of planetary formation and evolution. For example, by studying the magnetic fields of red dwarfs and their influence on planetary atmospheres, researchers can gain insights into the conditions necessary for life to flourish on exoplanets. The study of planets like OMIC B provides a unique opportunity to observe the effects of stellar winds and radiation on a planet's atmosphere in real time, offering valuable data that can be applied to other planetary systems. As we continue to explore beyond our own solar system, the potential for finding habitable planets around red dwarfs remains an exciting prospect. While the harsh conditions posed by these stars could limit the chances for life in some cases, they might also reveal entirely new forms of life and environments that we have yet to imagine. The exploration of red dwarfs and their planets is not only advancing our understanding of the universe, but also expanding the boundaries of what we know about the potential for life in the cosmos. Whether these distant worlds can support life remains uncertain, but the journey of discovery is just beginning. The quest to understand the relationship between red dwarf stars and their planets is a crucial part of modern astrophysical research. As technology continues to advance, we can expect to learn more about the intricate and sometimes unpredictable interactions between these stars and their planets. The story of planets like OMIC B, with its dramatic atmospheric changes, is just one example of the many mysteries that await us in the far reaches of space. While these findings may challenge our understanding of what makes a planet habitable, they also remind us of the immense possibilities that exist in the vast universe. The continued study of red dwarf stars and their planetary systems opens up a realm of possibilities for scientific discovery. These stars, being the most abundant in the galaxy, represent a vast reservoir of potential habitable worlds. While their environments can be hostile, they also challenge our preconceived notions of habitability, pushing scientists to explore novel concepts of life and survival. Future missions, such as the Nancy Grace Roman Space Telescope and proposed projects like the LUVOIR, Large UV Optical Infrared Surveyor, will complement the James Webb Space Telescope by expanding our capacity to detect and analyze exoplanets. These tools will help uncover detailed information about planetary atmospheres, surface conditions, and even signs of biological activity. Beyond technological advancements, interdisciplinary approaches will play a crucial role. Collaboration between astronomers, planetary scientists, biologists, and chemists will be essential to decode the complex interplay of factors that make a planet hospitable or not. Laboratory simulations and computer models will help replicate the extreme conditions of red dwarf systems, offering insights into atmospheric dynamics, chemical reactions, and potential biosignatures. One area of growing interest is the possibility of shadow biospheres, hidden forms of life that may thrive under conditions vastly different from those on Earth. Red dwarf planets, with their unique and extreme environments, could harbor entirely new biochemical pathways and ecological systems. The discovery of such life would revolutionize our understanding of biology and redefine the parameters of habitability. Moreover, studying red dwarfs can shed light on broader astrophysical processes. These stars have long lifespans, often exceeding tens of billions of years, providing stable environments for planets over immense timescales. This longevity increases the likelihood of life developing and evolving, making red dwarfs prime targets for exploration. Despite their promise, challenges remain. The high variability of red dwarfs, characterized by frequent flares and stellar winds, raises questions about the long-term viability of life. Researchers are also working to refine methods for distinguishing between false positives and genuine biosignatures when analyzing exoplanet data. As humanity's gaze extends further into the cosmos, the study of red dwarf systems embodies both the excitement and complexity of our quest for extraterrestrial life. Each new discovery adds another piece to the puzzle, revealing a universe rich in diversity and potential. Whether we find life in these distant systems or not, the journey itself deepens our understanding of our place in the cosmos and the extraordinary possibilities that await.